Hi. So what about the delete operation as far as the AVL tree is concerned? I'm not going to implement it from scratch because basically this part is exactly the same as we have seen for the binary search tree remove operation. And that part we have implemented from scratch. This is exactly what we have been talking in the theoretical section in the previous lecture, that basically we have to do two things. First, we have to make a simple binary search tree remove, and after that, we have to make sure that we settle the deletion violation. Basically, we have to check whether the tree is balanced or not. So as far as the delete method is concerned, we have a recursive method call, so we have to define a base case. If the node is equal to null, then we return null basically, so we return the node. First, we have to look for the node we want to get rid of. I make several comments to make it as straightforward as possible. So if the data is smaller than the node we are standing, we have to go to the left recursively. So that's why we call the setLeft node and the delete method recursively. Else, if the data is greater than the node we are standing on, we have to go to the right. Else, what does it mean? That we have found the node we want to remove. We have three cases as we have discussed in the theoretical section. If it is a leaf node, we just have to set it to null. So if the left child is a null and the right child is a null, it means that it is a leaf node. We just return null. It's going to be returned, and this is going to be replaced with a null, so we set the left node or the right node to a null accordingly. If the left node is a null, we know for certain that we have a single right child, so we have to remove a single right child. We update the references, so we get the right node, we set this node to be equal a null, and we return with the temporary node. Else, if the right node is a null, we know for certain that it must have a single left child. So we remove a single left child, we update the references and return with the temporary node, which is going to be placed here because it is a heavily recursively implemented delete method. Else, we know that it's going to be the situation with two children. So first we have to get the predecessor. I have already implemented this method. We just get a temporary node, this predecessor, and while the right node is not equal to null, we get the next node as far as the right subtree is concerned, and then we return with the predecessor. What does it mean, the predecessor? It is the greatest item, the greatest node in a given subtree. So that's why we get the predecessor on the node left node. As we have discussed in the theoretical section, we have to find the greatest item in the left subtree. So that's why we get the left node, and the predecessor is going to get the greatest item. So that's why we look for the right node, because the right node is the greater, left node is the smaller. Okay, so we get the predecessor. We swap the two nodes, and then we call this delete method recursively. Okay, so that's why we set the left node, because basically we have to consider the left subtree, because we know that we have swapped the given node with the predecessor, and the predecessor is in the left subtree, and we have to call this method recursively. Okay, then we have to update the height parameter, and then we have to check on every delete operation whether the tree has become unbalanced or not. So that's why I'm going to return, and before returning the given node, we have to call this settle deletion. And the settle deletion is going to be very similar to what we have discussed in the insert method. We get the balance. If the balance is greater than 1, what does it mean? What is the getBalance method? It's basically the difference between the height of the left subtree and the height of the right subtree. So if this getBalance is greater than 1, what does it mean? That it is a left-heavy situation. But we have to decide whether it is a left-right heavy situation or a left-left heavy situation. So it's going to be a left-right heavy situation if this getBalance on the left subtree is again smaller than 0. So if the get balance on the left node is smaller than 1, what does it mean? That basically the haste of the right subtree outperforms the haste of the left subtree, so it is a right-heavy subtree. So basically we have checked whether it is a right-heavy subtree in a left-heavy subtree, so it is the left-right-heavy situation. We have to make a left rotation first, and then we have to make a right rotation. But if we know that it is not a left-right heavy situation, we just have to make a simple right rotation. It is a very elegant implementation, by the way. We just check whether we have to make a left rotation before the right rotation, because if it's a left-left situation or a left-heavy situation, we just have to make a simple right rotation. Anyways, we have to make a left rotation and then a right rotation on the grandparent. Anyways, it's going to be approximately the same but quite the symmetric partners. So if it's smaller than -1, it means that it is a right-heavy situation, and we have to decide again whether it is a right-left situation or a right-right heavy situation. If it's a right-left heavy situation, we have to make a single right rotation on the parent and then a left rotation on the grandparent. If it is a right-right heavy situation, we just have to make a simple left rotation without the right rotation. Okay, so this is what we have been discussing in a theoretical section on a step-by-step basis. So this is how we make the deletion. Let's consider, for example, an example. We insert 10, then 15 going to be the right child of the root, then 5 is going to be the left child, and then 14 is going to be the left child of 15. So whenever we get rid of 5, we end up with a right-left heavy situation. So we have to make a right rotation on the, let me consider it, we have to make a right rotation on the 15, then a left rotation on the grandparent, which is the 10. Let's see whether it's working fine. Yeah, we have to make a right rotation on 15 and a left rotation on the 10. What if we consider, for example, this 10, then the 15, then 5, and we have 20. If we get rid of 10, then we end up with a right-right heavy situation, so we have to make a single left rotation on the 10. Okay, what if the same, but instead of, for example, we have the 5, we have the 15, we have the 5, and we have the 4. If we get rid of the 15, then we end up with a left-left heavy situation, so we have to make a single right rotation on the root node, which is the 10. Okay, it's working fine. What if we consider the last situation? Basically, we have 10, 15, 5, and for example, 6. If we get rid of 15, we end up with a left-right heavy situation. What do we have to do? We have to make a simple left rotation on the 5 and the right rotation on the grandparent, which is the 10. So, left rotation on 5 and right rotation on 10. Okay, so this is how the deletion works. Thanks for watching.